Okay. Gentlemen, I'm pleased to be able to deliver the third of a series of 3 lectures. In the first one, I gave a general overview of shell stability analysis. In the second, I introduce you to DISDECO, the Delft Interactive Shell Design Code, which is an effort to make available to shell design specialists the accumulated analytical, numerical, and theoretical knowledge. And in this last lecture, I shall address myself in detail to one of the computational modules. As I discussed it in that lecture, that is a series of computational modules in an interactive environment. And today I shall address myself to a level 2 module, which contains Coiter stability theory, but then extended to the buckling of anisotropic shells and with nearly simultaneous buckling modes. So I'm essentially following Coiter's way of looking at problems, but both of those extensions are new. I shall want to recognize the 2 co-authors who are students who did their master's thesis with me and have contributed to this effort. On the next slide, I essentially like to point out to you why we got interested into nearly simultaneous buckling modes. In a 1982 lecture at the UTAM symposium, I covered in general the buckling of different types of shells using different types of approaches to it, and I discovered the phenomena that is depicted on this picture here. What do we have here? We have a Stringer-Stiffen shell with C4 fully clamped boundary conditions, and what you see here is the B factor, which when it is negative designates that the structure is imperfection sensitive. Here are the parameters of the stiffeners that have been used by Hutchinson and Frauenthal in their 1969 Journal of Applied Mechanics paper, and they plotted the results versus Butt-Off Z parameter. And remember, Butt-Off Z parameter can be looked upon as a measure of how long the cylinder is, because if you assume that you keep R and T, the radius and thickness, constant, then the variation of L, the length squared, puts you either in the short shell region or the long shell region. I show you here the curve obtained by Hutchinson and Frauenthal in 1969. I used a code called SRA by Jerry Cohen, which essentially has the safe capabilities, and I tried to reproduce their results, and I went a little bit further, and I discovered that at a certain Z parameter value, I get what appears to be a peak in the imperfection sensitivity. The more negative B is, the more imperfection sensitivity is. Looking at it more carefully, it appeared that points on this side of the curve had a symmetrical buckling mode in the axial direction, number of waves in the circumferential direction, and the ones on the other side had anti-symmetric. So essentially it appeared that at this point here you had nearly simultaneous buckling modes, and for that the simple Coiter theory is not applicable. It has to be redone. Also, in aerospace engineering, one is at this moment very heavily interested in the so-called anisotropic shells. Those are composite shells made of all kind of fiber reinforced materials, build up the wall in different layers, and you can essentially tailor your strengths very conveniently. I have written here Donnell type shell equations. I have discussed already in my previous lectures. The nice thing about this approach is that the right hand side remains the same as before, and the anisotropic comes in by these linear operators, which are shown on the next slide. And essentially the difficulty comes because of the presence of these terms that involve odd-numbered derivatives, 3 with respect to x, 1 with respect to y, 1 with respect to x, 3 with respect to y. I also indicate here the well-known nonlinear operator that appears in Donald-type shell equations. Now, the asymptotic perturbation expansion that was proposed by Koiter many years ago, and its modification in order to be handled nearly simultaneous buckling modes. Essentially, the variables of the problem are the normal displacement W, the Airy stress function F. We have a perturbation expansion. The perturbation parameter is the amplitude of the buckling mode. And the modification here is that since there are more than one buckling mode, which is active, we sum over them. So essentially, the repeated lowercase indices here imply summation. The consequence is that you also have to sum over the second order field. So essentially, you end up with many of these, as many as are nearly simultaneous modes, and then that much more there. Here is the well-known form that is used to describe the load deformation behavior. These are the first post-buckling coefficients. These are the second post-buckling coefficients. There are as many of these equations as there are buckling modes. Notice that there is no summation implied over repeated upper indices, only over repeated lowercase indices. No summation, okay? You might think there is a summation, but there is no summation over uppercase indices. Okay, now you know how this thing works. You take your perturbation expansion, you shove it into the governing equations, you group them according to powers of the small parameters. The pre-buckling problem is C to the 0th power. It looks then essentially precisely the same as the equations before. They have one advantage when one tries to solve them. If one assumes that the external load is axisymmetric, uniform, if one assumes that the boundary condition is axisymmetric, uniform, then the pre-buckling problem is essentially axisymmetric. So essentially, with these assumptions, we can reduce these equations to one fourth order ordinary differential equation in W sub O, first derivative, second derivative, etc. Notice the primes are normalized with R. Now, this is a constant coefficient equation. So you can write down its solution, right, in terms of exponential. I do it numerically because it's more convenient, but there is no problem to it. Buckling problem looks, and as indicated here, the buckling problem is a problem for the first order field. It is a linearized equation for the first order fields. And notice here, here, and here, we have contributions of a pre-buckling problem. Now, if the pre-buckling problem is rigorous, then W super O and F super O is a function of X. And then here we have variable coefficient equations. The easiest way to solve them, assuming that the pre-buckling state is membrane. Then these quantities are constants, and since these operators always imply second derivatives, then their contributions here disappear with the exception of the load term. And then you have, for the stability problem, equations that are constant coefficients, which are considerably simpler to solve. Now, I indicate here then the solution, how the solution proceeds if I am assuming that I'm using rigorous pre-buckling. I substitute the pre-buckling solution, which is axisymmetric, and then I keep those terms as variable coefficients in my stability equation. I solve then the stability equation by this approach. I know that when the shell buckles, I get a buckling pattern with a number of full waves in the circumferential direction, which I can express by cosine ny over r or sine ny over r. I have to have both cosine and sine because the problem is fully anisotropic to account for the skewedness. And if I take this assumed form, where I have here now unknown functions, and substitute them in the previous partial differential equations, and those can be reduced to n sets, one set for each eigenvalue, of 4 linear homogeneous ordinary differential equations with variable coefficients. So I have essentially n eigenvalue problems. N is a number of nearly simultaneous modes. The problem is then solved numerically. Let us look at the post-buckling problem. The same substitution business. You have here the operators for the second order fields, and then at certain locations the pre-buckling solutions come in, and I also pick up parts that have to do with the buckling modes. So essentially the form and shape of the buckling modes have an influence of what type of second order fields I get. Notice that these equations here are inhomogeneous, right? Because I can put all the terms that involve second order fields over to the left side, I still keep this one and this one on the right hand side. So this is not an eigenvalue problem, but a response problem. I first have to solve the eigenvalue problem to find the eigenmodes. Then I have the forcing function. I have to solve these equations, once again numerically. Now, I just indicated how this looks. If I substitute that, I mean, it's no big problem to write those things down. You also have such very nice tools to check your algebra, like Maxima or Maple, or you name it, Reduce. And besides, they have a, this is in the equilibrium equation, they have a certain logic to them. It is, if you have written down a couple of times, if somebody misses the order, you very quickly discover that something is missing. But anyhow, these are the equations that you have to solve. Okay, now, to solve them, once again, if you look at it long enough and you study the literature, not fully anisotropic, but orthotropic or isotropic problems have been done before. Those are subcases of this. You will see that, once again, you can separate variables. Here you have functions that depend on y, which are known, cosines or sines. And here you have unknown functions. So essentially, the same thing, what we did with the buckling problem, we repeat with this one. Upon substitution and regrouping, we get n minus 1 times n sets of 8 linear inhomogeneous ordinary differential equations, also with variable coefficients. And we have also n minus 1 times n response problems, which we have to solve. Now, let us now look at, since we are interested in the imperfect structure, the behavior of imperfect structure, you know, Coite's idea was that if the imperfection is sufficiently small, then he does a Taylor series expansion of the behavior of the imperfect structure at the bifurcation point of the perfect structure, and he hopes by this Taylor series, by keeping the first or maybe the second order term, to get enough information about the location of the limit point. Now, this was the expansion for the perfect, and this is what is added to it to account for the imperfect structure. Notice there comes in an alpha coefficient and there comes in a beta coefficient. These are the so-called imperfection, first and second imperfection form factors. They take care of what happens. I mean, you can assume that the initial imperfection has precisely the shape of the buckling mode, then alpha and beta will be 1. But it could be that you don't want to, you measured the imperfections and they have a certain form. And that doesn't agree with the form of the buckling mode. You still want to use Coite's theory. You can. But then, when you calculate the coefficients alpha and beta, they will not be 1. They will be some other number. Essentially, this idea of introducing the first imperfection form factor has been done in that paper by Hutchinson in Frauenthal. And the second imperfection form factor was introduced by Cohen when he derived his code SRA. Notice the error that you make. It is of the order xi, xi bar. Terms of order xi, xi bar are neglected. Very important to remember when you interpret some of the results. Once again, no summation of the upper case indices. There are as many of these relationships as there are active buckling modes. Now, I will give you some detail what these coefficients look like. There will be rather elaborate formulas, and in order to be able to get them on a slide, I will have to use the shorthand notation. The shorthand notation was once again introduced by Frauenthal and Hutchinson in their paper. And if you look at it, I will use a symbol that looks like this: sigma star, L11, and two arguments. What does that mean? That stands for a surface integral over the mid-surface of the shell, and it always involves product of three terms. It depends what you put there. I mean, if you recognize that, that is the stress resultant of the buckling mode. Stress resultant, stress resultant, stress resultant, super 1, buckling mode. If you look at that, that is the out-of-plane displacement of the buckling mode, right? Derivative of it, okay? Those. And that double subscript, that is a second order field in derivative forms. So this shorthand notation stands for a rather extensive expression. Now, okay, first, post-buckling coefficients. If you derive them, there are different ways of doing them. Best reference is how to do it with this notation that I'm using from the Harvard School. Is a paper by Fitch on buckling of spherical shell. That contains a complete derivation. I think that's the most complete reference at how these derivations are done. Now, here are the first post-buckling coefficients that I want to solve for. And notice, they have to be solved for simultaneously. Also, I cannot solve for one, I have to solve for all of them at once. And whether they are coupled with each other or not depends on how big the off-diagonal terms are, right? If only the diagonal terms are occupied, then they are uncoupled. You can solve one by one. If the off-diagonal terms have contributions, then they are coupled. Now, what these different symbols are is given here. This here is given there. Notice they involve those shorthand notations. There's something else that appears here. You have here a sigma c. That is the stress resultant of the buckling mode evaluated at the bifurcation point, and you have a dot. Now that is dd lambda, derivative with respect to the buckling load. Remember, we do a Taylor expansion around the bifurcation point. There is once again here also. Notice also that, for instance, these terms here, what is that? That is a buckling mode evaluated at the bifurcation point. If I'm using membrane pre-buckling, then this is 0 and this is 0, so these terms disappear. If you use rigorous pre-buckling, they exist. This is here a second post-buckling coefficient, written in a similar form. Here it is. This is the right-hand side. Notice that now, if I have non-zero first post-buckling coefficients, they appear as a forcing function when we solve for the second post-buckling coefficient. And here I am summing over the uppercase index I, but I'm indicating it separately. Okay? Now, luckily, in most applications, cylindrical shells, etc., the A's are 0, so I don't have to worry about these in general. I only have to worry about those. Bad enough, if you look at it, they are rather complicated looking expressions. Once again, if you have membrane pre-buckling, U is constant, and this is 0, and that is 0, so certain simplification occurs. First imperfection form factor, a similar expression. Remember what I said. If they are uncoupled, then only the diagonals are occupied and the rest is 0. Notice that here, in here, there is U cap. U cap. U cap is a functional dependence of the initial imperfection. It may be equal to U sub c, but it doesn't have to be, right? So the initial imperfection, you decide. It has an amplitude and a form. If the form does not agree with the buckling mode, then the alphas will be no different from 1. Otherwise, they'll be 1. Here you have the second imperfection form factors. Once again, the interesting thing that the second imperfection form factors have on the right-hand side the summation over the first imperfection form factors. Notice here there are now double dots. Those are second derivatives with respect to the eigenvalue. And there are some complicated looking integrals which are indicated there. Okay, now it's mostly so that when you do more involved, more refined analysis, there are papers in the literature where people have done similar things with simplifications. As a matter of fact, investigating the effect of nearly simultaneous buckling load has been done by Biskov from Denmark and Hutchinson. They have assumed membrane pre-buckling. If you assume membrane pre-buckling, then uc is a constant. Sigma c of lambda becomes lambda times sigma c, so it is the eigenvalue appears as a multiplying factor, and then this symbol here that you have seen before can be written in this form, and it is 0 because this expression here expresses the fact that the different buckling modes are orthogonal. Okay, so if we use that simplification, then the previously shown formulas reduce to these forms here, where for membrane pre-buckling you can show that this here is equal to that symbol used by Hutchinson and Biskov and Hutchinson, and essentially these are precisely the expressions that they have obtained in their paper 1977. It was published in the AIAA journal. Okay, now going back to the second slide, I said to you, how did I get involved and thinking about this? Is it because that particular shell of Hutchinson's, when the length had a particular value, giving a certain z, was exhibiting kind of the existence of nearly simultaneous modes. Okay, now, if you do a study of different buckling modes, if you solve for simultaneous buckling modes, I have to say here, I didn't say anything about the numerical method used. Maybe I shall say here a word. The response problems, which is a pre-buckling problem and the post-buckling problem, is solved by standard shooting method, parallel shooting about a certain number of intervals that are needed. The solution of the nearly simultaneous eigenvalues and eigenfunctions is done by a subspace iteration, which seems to be very efficient because we have been able to pick up without any problem buckling modes and buckling loads that were practically simultaneous. You will see it. For instance, here, to this scale, there are two of them. One on the symmetric, in the axial direction symmetric, and one in the axial direction anti-symmetric. I always like to work with rho, which is a kind of a normalized eigenvalue. What I do, I take the eigenvalue and I divide it by the lowest value, which here is 15.3028. This here is the number of waves in circumferential direction, and I will look at n is equal to 8. There exists a symmetric and there exists an anti-symmetric very close to each other. What do they look like? Here they are. The anti-symmetric is essentially the lowest, 15.4328, n is equal to 8. It is Hutchinson shell with medium stiffening according to his designation. It is fully clamped C4 boundary condition, and at x is equal to L over 2, I'm only plotting half of it. Of the buckling mode, I'm using anti-symmetry. So the buckling goes like this and comes back like that. This is a pre-buckling solution. It is axisymmetric. This is a buckling solution with n is equal to 8 waves. And this is a post-buckling solution which has W alpha and W beta. No W gamma, because this is orthotropic shell and there is no skewedness in the buckling pattern. Notice these here are normalized by their maximum value. It is so that W sub alpha is normalized by 0.040 and W beta is normalized by 0.321. So W beta, which is a dashed curve, if I didn't normalize them, would be 10 times as big as this one. And probably you couldn't see it if I put it onto the same plot. Okay, so this was at 15.4328. The next one is 15.4484, the symmetric. Also n is equal to 8. Here is the pre-buckling is the same. Here is the buckling, which is now symmetric. Here is the post-buckling. Okay, so we have them. What you do then, here is the first one, here is the second one, very close to each other. Then you have two equations for describing their behavior in the lambda Xc1, Xc2 plane. And here we, to make it a little bit simpler, wrote it down for membrane pre-buckling. So the alphas and betas are 1, so their effect disappears essentially. These are the B's that were non-zero. The super 2 here doesn't mean that it is squared. Remember, we have an uppercase index which designates whether it belongs to the first buckling mode or to the second buckling mode. Maybe one should put that into parentheses, but just pointing out, is not much doubt what that is, but this is not squared. Okay, how do you solve that? This is a space curve. Luckily, we know that it starts, the curves that we are interested in, starts at lambda is equal to 0, no load, no deformation. So we start at the origin of the axis. And then we using Rick's path following technique to find the limit point. You just climb up on it and find it. It is a question of seconds even on a PC to do it. For two active modes, you can even represent it nicely. So what we did here is a vertical axis is a load normalized. So actually the perfect shell buckles at 1. Here we have put in imperfections in both of them. And essentially what you get is a space curve that comes up here and turns around. Now, you also see the traces of this space curve. If you want the trace looking in along the Xc1 axis, then you see the trace in the lambda Xc2 plane. That is it. If you want to see the trace looking in along the Xc2 axis, then you have the trace in the lambda Xc1 plane. There it is. If you want the trace looking from the top, you see the trace in the Xc2, Xc1 plane. There it is. Okay? But you are interested in where the limit point is, right? Because you calculated the B factors for the structure and you have inputted a certain imperfection. So you want to know what is its effect. And essentially, as I said, to perform this operation, even on a PC, takes you 2 seconds maybe. It's a very quick operation. You don't notice it practically. Okay, now let us move one step up. I increased the length from 3.440 to 3.450, and now I am on this side of the curve. Symmetric is the lowest, anti-symmetric, now they are a little bit farther apart on this scale. So now I'm looking once again on these two. Once again, the lengths, the boundary condition, where the eigenvalue is the lowest, which is symmetric, right? Symmetric. This is a pre-buckling solution, post-buckling solution. Then the next one, 15.2348, 15.3936 is the anti-symmetric. The pre-buckling is the same as before. There is a post-buckling field. And then essentially what you have to do, you have to solve this set of equations, right? The eigenvalues are now somewhat different. Essentially the same terms are non-zero. You once again do path following technique. Now, the other things you might wonder, okay, now how can I represent this information? What we have tried here is the following. We said, okay, essentially we have a three-dimensional space. Here you have rho, that's lambda divided by the lowest value to normalize perfect shell behavior to 1. Here you have Xi1, and here you have Xi2. We set Xi2 equal to 0.2. So even when Xi1 is 0, you still have Xi2 equals to 0.2. So it will bifurcate here. And then as you increase also Xi1, you get the limit point and you get this type of behavior. Extra points for Xi1. So Xi1 0, Xi1 1. Xi1 1 means 1 wall thickness. You can also, if you wish, just set it one of them equal to 0 and just look at the other one. These type of curves exist in the literature, right? Just a single mode. You can check whether that works. Now, I have advertised that the code that we developed can do anisotropic shells, right? I mean, before what I showed you was essentially the example that triggered it, an orthotropic shell by Hutchinson. Now, this is a boron epoxy shell, which I call Cott shell because I took out of a report of Cott. Cott is the chief scientist, was the chief scientist in 1970 at the Wright-Patterson Air Force Base. I don't know precisely whether he has meanwhile retired or still there. But anyhow, it is a shell that he has used. It consists of 3 layers. The outer layer is at minus 40 degrees, the next one at plus 40 degrees, the inner layer at 90 degrees. Boundary condition is classical simple support. And we found the first eigenvalue at 20780 with 11 waves. We are using nonlinear pre-buckling, so you see here the Poisson's effect, and here you see the edge effect. This was a shell that was 12.5 inches long and radius 6 inches. So L over R was 2, rather long. And so most of the shell, you have the membrane solution valid, and only at the edges, the edge effect. Looking at the buckling modes, this is the one that has edge buckling. I mean, the buckling mode is really, big deformation is close to the edge. Remember, this is not axisymmetric. It has n is equal to 11. So it has 11 waves in the circumferential direction. But for the most of the shell, you have nothing in the buckling mode. All deformation is concentrated there. You immediately, I'm using here symmetry here. You should immediately suspect, if you are an analyst, that there is a second one anti-symmetric, because it takes practically the same energy to flip around to the other direction. So indeed, now let me see, 20780, there is another one at 20781. So my comment about using subspace iteration, you can pick up practically simultaneous modes. This is one because, look, I mean, the difference between the two is only in the fifth digit. This naturally looks precisely the same. This very much looks the same, right? Only here, if you look very carefully, you will see that the other one was anti-symmetric, this is symmetric. Okay. Now, let us see what happens when we start looking at its different effect. This is alpha and beta is set equal to 1, Xi2 is 0, so this is just the effect of having Xi1 varying from 0 to 1. And this is a type of curve, it looks very much like Coitus curve. It knocks down quite a bit, just the presence of that one imperfection. Okay, now let us look at another case. I have now set Xi2 equals to 0.2, alpha beta still 1. Here varies from 0 to 1 Xi1. So notice the other curve that came down here. Now, since Xi2 is equal to 0.2, I start here, and then as Xi1 increases, this kind of asymptotically approaches the other curve. So here interaction effect is only restricted to this region. The rest of it, the presence of one or the other, has about the same effect. Now, I have here a comment about the fact. You might ask, what about the effect of alphas and betas? Now, essentially, the slides that I am showing you are the ones that I used for a lecture at the UTAM Congress in Israel. That was in August. At that time, that was all the data we had. We have not, at that time, calculated alphas and betas, so I couldn't show any results with alphas and betas. Meanwhile, I have done considerable work on it, on a NASA contract, and it is very interesting that what the values of these quantities are, it has a very big effect. Now, there is an old paper by Jerry Cohen, a NASA contractor report, March 1973, where he studies and shows the effect of the first and the second post-buckling coefficient. Remember, he introduced the second post-buckling coefficient, so he obviously had to show why is that important. Now notice the following. This is for a single buckling mode, so this is the equation. If you want the limit point, at the limit point, d lambda dxc is 0. So you have two conditions, and combining these two, you can write the location of the of the limit point by this formula, which is essentially a modified form of Koiter's formula. Koiter has only done cases where beta and alpha were 1, so if you introduce here beta over alpha equals to 1, then that one cancels against this, and you have exactly Koiter's formula that he has published. Okay, let us study this a little bit. Here you have what I call rho always, lambda s, that is a load at the limit point, divided by lambda. It should be actually lambda sub c. Lambda sub c. Okay, that's an error here. Lambda sub c, and there also should be lambda sub c. This is that rho that I am always using. Okay, so if you have a perfect shell, then the value here is 1. It is to the 3/2 power. Then you have here the square root of minus 3 alpha squared, the first imperfection form factor, times b. Now this is what Hutchinson and Frauenthal had in their paper. This is the new thing that Jerry Cohen introduced, and we shall see on the next slide what the effect of it is. Okay, so if you look at it and you say, okay, I have only alpha, and beta, let us say, is the same, how is it plotted? On the vertical, you have rho sub s. Rho sub s is lambda s over lambda c. Okay? Where is the limit point? Notice this is on the logarithmic scale. Here you have 0.01, so that essentially this curve goes to 1 somewhere out there. Here you have, if you look at it, it is b alpha squared c bar squared in parentheses to the 1/2 power. Notice here is a minus, and it indicates essentially that you only have an imperfection sensitive structure if b is negative. If b is positive, there is no effect of imperfection because here you get an imaginary number. Okay, now if we have the situation alpha is equal to beta, then we are working with this curve here. And notice what happens, that if you work with that curve, it seems for very large imperfections to indicate, right? For very large imperfection, it indicates that the shell will have no load carrying capability whatsoever. Obviously not true. If you are an experimentalist, you know even a very imperfect shell will carry some load. What is on the hand? Now remember that in the formula we neglected terms of order c bar, right? So essentially, the validity of these curves is only up to a certain value of this parameter. And notice how important it was to introduce a beta, because if you calculate also beta besides alpha, and you are falling into those type of curves where the ratio beta over alpha is bigger than 1, then essentially beta brings this curve back to approaching an asymptote. So that essentially, that seems to be better describing the physical fact that, I mean, there are certain sizes of imperfections beyond which the shell will, never mind whether you change the form of the imperfection around, it will always carry about the same amount of load. So essentially, the introduction of this beta from Jerry Cohen made it possible to extend the range of validity of this asymptotic method. Because if you don't use it, as I said, that it will show here that it goes to 0, and you obviously know that's incorrect. Okay, if I have it right, yeah, I have just the last slide, which I already showed you. The question always then arises, how accurate are asymptotic methods, right? And I have shown you these slides before in other lecture. Essentially, I'm once again working with rho. I'm dividing the perfect shell, the buckling load of the shell by the perfect shell buckling load. So bifurcation of the perfect system occurs at 1. With the asymptotic method, we describe the behavior close to here. If you really want to know how accurate is your asymptotic method, you have to go to higher order modules and essentially calculate the post-buckling curves with a code where the errors are not of order xc bar, but higher, right? And then you can compare the two. And for instance, what you have here is a pre-buckling curve. Perfect shell bifurcates there. Immediately after bifurcation, the slope of the post-buckling path is negative, so you expect it to be imperfection sensitive. And if you calculate, if you step over onto this branch and you calculate it, you notice that the slope becomes more and more negative, right? And then it comes back again. So that if you put in an imperfection, you get, for an imperfection of size of 1 wall thickness in the shape of the buckling mode, a 40% decrease in the load carrying capability. Well, thank you very much. I think that is the description of this module, which is called ANOFSI. It is not in this deco yet, but it very shortly will be.
Are there any questions? Okay, I have a question, of course. In hot shell,
Yeah.
What was Hoth's result for buckling? Probably he did not take into account simultaneous buckling modes. And what is your correction?
Well, Koth essentially developed.
Can you repeat the question?
Yeah, okay. The question was, I have presented results of Koth shell, and I have studied the imperfection sensitivity of it. And the question was, what were Koth's results? Now, Koth's shell was presented in a report by Koth where he studied the B factor, he applied the B factor to anisotropic shells. He used membrane pre-buckling, contrary to here where I'm using rigorous pre-buckling. So essentially you could say that his results were level 1, and these results that I presented to in terminology of this deco are level 2. As it turns out, in this particular situation, Koth's predictions are much more. He predicts that the shell can carry far less than what I predict with this method, and that comes because in his method, the buckling modes are also different. He gets for this one an axisymmetric buckling mode, and then he has to go, he cannot use B factor, he has to go to looking at imperfection sensitivity for axisymmetric imperfections, and he will, for this particular shell, if he goes to an axisymmetric imperfection with 1 wall thickness, predict a bigger decrease in buckling load. But this is the example where I think yesterday I warned about. Whenever the level 1 solution gives you a buckling mode which is axisymmetric, you should immediately have something click in your mind and say, aha, I better repeat it with nonlinear pre-buckling because probably I have edge buckling, asymmetric mode, and that's precisely what happens here.
What is the difference between application of your methods with simultaneous buckling modes and without simultaneous buckling modes numerically?
Well, we do not have enough information yet to make a categoric statement. It is definitely so, as I have shown you on the examples, whenever there are 2 of them present, you get a bigger decrease. So essentially, what does that say? That peak that appeared in the second slide, which started this whole work, is actually there. Maybe it is even more pronounced. And why is it there? Because you get nonlinear interaction between nearly simultaneous modes.
So that how does that figure which you started, you mentioned the figure which you presented in 82,
yeah, okay,
modify?
Well, it will be deeper.
Can you just show by
Yeah.
it will be even deeper?
Yeah. So we had a plot like this. Here you had Z, L squared RT square root 1 minus mu squared. Here we had B, 0, minus 0.1, minus 0.2, etc. And we had a situation at a certain Z value, I think it was around 400. So this here is somewhere around 400, where we had a curve coming from here and a curve coming from there. And I said, look, this one here in the axial direction is symmetric, and this one here in the axial direction is anti-symmetric. And then the question was, what happens here? Right? The analysis that I have been using to plot this curve only was based on single mode. So with this method here, what I presented, we take into account that very close to this curve, both of them are, and essentially our preliminary conclusion is that indeed you get a very steep peak there, because you have two of them and they reinforce each other. Just how steep and just how big, I mean, I will have to run more cases, and it will come in the written paper.
You may want also in that paper of yours find the lengths at which the coincidence of the eigenvalues is perfect, not up to fifth digit or fourth digit, or because you had the length, you were increasing the length, and you had eigenvalues more spread out, so you can decrease a bit the length and find some critical lengths, and you see what happens. And then when you will find that length, maybe you will be surprised. Why do you have such a big imperfection sensitivity there? Because you will get even steeper.
Well, I mean,
may you repeat the question?
Yeah, the question was whether we could vary the length such that the two eigenvalues will precisely fall on the top of each other and thereby establish a critical length. I think that certainly when the paper is written will be one of the conclusions, that if you design a shell, you will have to make an investigation. Are there any lengths where you will have the occurrence of nearly simultaneous modes? It depends strongly on the shell parameters. I mean, it is different if I change the stiffness parameters. So I cannot derive, say, a string-stiffened shell always at that length. It has this type of occurrence. It has to be investigated by the analyst because it depends on the stiffness parameters. But certainly that will be one of the conclusions, that look, there is this possibility. You have to watch it, because indications are that because of the nonlinear interaction of the nearly simultaneous or simultaneous buckling modes, you get an increased imperfection sensitivity. Now, what one has to caution there, that this increased imperfection sensitivity occurs for imperfections in the form of the buckling modes. Right? So imperfection 1 has to be precisely symmetric, imperfection number 2 precisely anti-symmetric. Okay? But certainly that will be one of the conclusions that has to be drawn from this investigation if in the end such a result comes out.
How much is beta over alpha in your analysis? Koiter put it to be 1.
Yeah, for membrane pre-buckling, if you use membrane pre-buckling, beta and alpha are both 1.
Yeah, but how how much?
In my analysis, I had cases where beta was negative, so it varies with the shapes. You see, it accounts for, you see, what I do in this NASA paper, which I just finished, I look at two types of imperfections. I mean, W bar, I write it, let us say, model 1 is wall thickness times W1 of x cosine n theta, W2 of x sine n theta. So notice these functions here are the buckling modes. So if I use this imperfection and calculate alpha and beta, then the initial imperfection is affine or similar to the buckling mode. Since I have done a lot of measurements, I am also interested, here I am missing an amplitude, right? H C bar sine k pi x over L cosine n y over r, where this is an integer denoting of the number of full waves, and here this is also an integer denoting the number of half waves in the axial direction. And I am very interested, what I did there, I chosen this k to be 1, because experimental measurements indicate that in the type of shells that I have looked at it, that is always the biggest imperfection, with k is equal to 1, just half wave in the axial direction. Apparently, if you make shells, you get a bowedness either inward or outward into the shell. Okay? Now, this here may or may not be similar to the buckling mode. I mean, you have seen buckling modes of the stiffened shells where this was out and this looked like half-wave sine. Okay, then there is no much difference between model 1 and model 2. They are practically the same. If you look at Koch shell, there both of these are present. I have edge buckling. So that buckling mode, if I say similar to the buckling, that the imperfection is similar to the buckling mode, that imperfection is totally different from this one. And I get then also very different values for alpha and beta. But this is, I think, a very important tool for the analyst, because, as I said, all my measurements up to now indicate that these type of imperfections are the ones that are most often present. You very seldom, or if ever, will encounter that very typical edge buckling type behavior. A very, very particular imperfection shape. I don't say that you won't ever encounter it, but it's very unlikely.
Now about this Cohen's correction, one wonders how good that is, because on one hand analysis is asymptotic, on the other hand it allows to have sort of non-asymptotic properties, for big values, whereas the theory is good for response times imperfection is small, so that it is some mixture. One would say some maybe non-valid mixture.
Well, what is valid? I mean, you test it, his predictions, which are of a certain accuracy, you can always test it against more refined analysis. And that is why I always put up these pictures, right? I mean, strictly speaking, asymptotic analysis is only valid right there in the neighborhood, okay? But engineers...
These two are close.
Precise. But you see, engineers always have the temptation, since they have to produce, right? They have to have results. They say, okay, now I make that circle a little bit bigger, okay?
So how good is really more a comparison between Cohen's prediction and just purely numerical approach?
I have not done any of those yet. I mean, that is one of the next activities. I have the codes to run it. As a matter of fact, I have a code which I written many years ago, which I call two-mode analysis, where I have an axisymmetric and an asymmetric imperfection. And there I keep terms up to and including Xi xi bar squared or xi bar. So these terms I keep. So you see there are 2 orders of magnitude better than if you look only at the order of what you have dropped than what I talked about. So I shall do this type of comparisons, and I expect that I have done periodically over the years, but not systematically. And essentially what the additional terms do, they pull the curve. You remember the curve went very steep down. Essentially these higher order terms, they come in when you are at larger displacement, and they usually turn the curve back up again.
More questions?
Dr. Harwood, I just wanted to know what is the difference between your results and the results produced by a gentleman called Vanduya. I noticed that in Vanduya.
What is the name?
Venkaya, maybe?
Vanduya?
You mean Venkaya?
Maybe Venkaya. This one?
I mean, there are papers, Kot
Cotton Venkaya.
and Venkaya.
Oh, yeah, probably.
You mean this?
Yeah.
Yeah.
As far as I remember, in 1970,
Yep.
1972,
Yep.
There were 2 gentlemen
Mhm.
who did the AEB analysis.
Yeah. That
on-
were those people.
Yeah.
Yeah.
So I noticed that in their reports, they ignore almost completely the boundary effect.
Sure.
Yeah. So now I understand that you use the level 2 approach
Yeah.
to deal with the same problem, but considering the boundary effect. How do you compare your result and those?
Look, what
Can
I
you
do,
repeat the question?
the question was, how does my results, which takes the effect of boundary conditions into account and rigorous pre-buckling, compare with Kot and Venkaya's results, who use membrane pre-buckling and use trigonometric functions which approximately satisfied SS3. Now, the best thing I can do is I send you a copy of this report. LR stands for Aeronautics Department 700, which I just finished. I have done there systematic comparison between Kot and Venkaya's results, because I have their method sitting in this deco as a level 1 code. So I can reproduce any of his results, or I can reproduce results for other shells which are of the same category, and then compare. In some cases, their predictions are very good. In other cases, they are less good. What does it depend on? It depends on, let me go back a little bit. I'm going in the wrong direction. Let me see. Yes, and I turn it to here. Yes, there it is. I should have it now. So let me see. Yeah, oh, that's prima. Look, it depends on the shapes of pre-buckling, buckling, and post-buckling fields that you get. Essentially, this deco is set up in such a way that you can run the module of Kot and Venkaya and plot these. Here, you get a straight line, membrane pre-buckling, right? Here you get the buckling mode, Kot and Venkaya. And here you get the post-buckling mode, Kot and Venkaya. Now, then you run my code, which I described, okay? And you look. Now, if there are not much difference between these predicted shapes, then your predicted alphas and betas and b's will be okay, because there are integrals involving these functions. If you get big differences, invariably, if you look at these shapes, let us say the effect here of the rigorous pre-buckling, or the buckling mode is completely different, okay? So there is not I cannot give you an answer categoric is always good or always bad. You have to run it And that is why we set up this deco the way it is, that you immediately can look if you see, oh, they are different. What is on the hand? You go back, you look at these shapes and you see it yourself. Aha, that is the explanation. And if you then have such a situation, which is then good? The more rigorous one, right? Because that takes the effect into account. And you see, the nice thing is, and that is what, makes also if you write a report like this and you get these different results, you have to explain them, right? And it makes it easy because you just look at these shapes and they are always there. If there is a difference,
Boundary effect is important.
in many cases, yes. Yeah.
Okay, if there are no additional questions, I will just make one remark that as the title of your first lecture indicated, actually future of stability analysis cannot lie outside stochastics because imperfections are there, they are unavoidable. They do not behave like they are described in papers, say 1 term or 2 term or 3 term, some numbers, but they are actually uncertain in their nature, and therefore one should deal with these uncertainties.
Yeah.
So I was pleased to convince you once that without these uncertainties, the shell analysis goes nowhere.
Mm-hmm. Yeah. Certainly. Yeah. And also, if I might add a last remark, the other day there was asked if you have very advanced codes, why look at the simple ones? You see, you have to have a bag of knowledge about a shell. And the only way you can get it, if you try first very simple, then a little bit improved, at the very end, then when you have decided this is what I want, then you go to the rigorous one. It doesn't work the other way, unless you are a very experienced person. Because then you already in the back of your mind, you have, this shell looks very much like the one that I analyzed 2 years ago. So then you pick up all that knowledge and transpose it. But otherwise, for instance, if I have to do a work for an outside source, I always do it by 2 different codes. Because it's very easy to make an input error. Right? you miss something and you are completely in the wrong ballpark. So you should always check and recheck. And things, if you do them right, they have to show, for instance, if you start with level 1, level 2, level 3, and you do it right, you should have a progressive refinement, and the changes from one going to the other should be kind of getting less and less. You should converge on a final result. Yeah.
I have another question.
Yeah.
Years ago, there is an argument about the sensitivity of the composite shears. Some people say that composite shears are less sensitive to the initial protection as opposed to the metallic shears. How do your recent results show?
Well, that's a very interesting question. Indeed, there has been argument about it. Yeah, the question was, there are people who say that composite shells are less imperfection sensitive than metallic shells. And essentially, if you look imperfection sensitivity, effect of imperfections consists of 2 things. One is the shape of the imperfection, B factor, etc. And then how big is it, right? Because you have seen these curves where you say for a certain shape, here is its amplitude. When there is no, I start at 1 if I have defined rho, and then it goes down this way. So essentially, one is how important is B, because that determines the precise shape of this, whether it runs there or whether it runs here, right? Different values of B give you different curves, but you also have to know how big is the imperfection, right? Now, essentially what is true, I think, is that composite shells, because of the way they are made, the techniques of having a very carefully made mandrel and then laying it up, composite shells are very perfect in the sense that you will find imperfections which are very, very small. And if they are very, very small, then it doesn't really matter that much which of the curves you are sitting on. You always get a very high agreement with a perfect shell load. So I don't think that they are less imperfection sensitive, depends on the construction. What is true, there are, by the way they are made, much more perfect. I mean, they are closer to being perfect than metallic shells.
What you say that Xi bar is very small.
Very small, yeah.
But maybe if we want to re-emphasize the question, for the same Xi bar, B is bigger or smaller for a composite shell versus
Yet once again, you cannot give a categoric answer. If I make a ring-stiffened shell, okay, and I calculate B for it, externally ring-stiffened shell, the B, and I take Cot shell, and I calculate B. Cot will have a B which is more damaging than the B that I find for the ring-stiffened shell, okay, from the Caltech ring-stiffened shell that was made out of aluminum. Still, if you look at Cot's overall performance, it probably will be better because this will be smaller than the one on the ring-stiffened shell.
No, what I mean is without ring stiffener. So we take isotropic shell without any ring stiffener, and then we take equal weight composite shell.
And once again, there are many configurations.
So do you want to say that for some configurations of composite shells, B will be bigger and for some maybe smaller?
Precise. Yeah.
So the answer is not direct, not.
You cannot make a categoric statement, one is less imperfection sensitive the other. You can well state, and I think that is correct, that overall, if you look at the overall performance, composite shells will come closer to the experiment, so to the theoretical buckling loads, if you run experiments, than metallic shells. Why? The Xi bar, in general, what I have seen is order of magnitude smaller, not a little bit smaller, order of magnitude smaller than on metallic shells. Metallic shells will always have imperfections of the order of the wall thickness. And the imperfection that you measure on composite shell will be always less than 10%. So it is an order of magnitude.
But this has a very interesting theoretical implication, because that means that for composite shells we can categorically say that asymptotic analysis performs better.
Yes, should. Yeah.
See, from design consideration we come.
Yep.
Okay, thank you very much indeed.
Yeah. Come.
And maybe